So now let's go over our ideal gas law problems. So in our first problem, you can see we have the number of moles, the volume, and the temperature. And we're looking for the pressure of this sample of gas, specifically in torr. Now keep in mind that the ideal gas law is going to give us the answer in atmospheres. So that means once we're done, we'll have to convert. So here's our ideal gas law. And it's really a matter of personal preference. Do you want to solve for what you're solving for after you've plugged the numbers in or before? A lot of times I find it's easier to do it before. We're trying to solve for pressure, so that's P equals nRT over V. Then we need to look at each of our terms and determine what, if any, unit conversions we need to do before we can actually solve the problem. So our number of moles is already in moles, so that we can use as is. R is the constant, that's as is as well. The temperature is given in Celsius. We need to convert that to Kelvin. And the volume is given in liters, which is where it needs to be also. So if we solve that, we find that the pressure is equal to 3.248 atmospheres. Last step, because we asked for the answer in torr, is to convert that to torr. And we should get 2,469 torr. So our next question has two parts. In both cases, we're looking at 1 mole of an ideal gas. In the first case, we want to find it at STP. So V equals 1 mole times R STP, if you recall, refers to 0 degrees Celsius, which converts to 273.15 Kelvin and 1 atmosphere of pressure. So the volume here, when we calculate this, is 22.4 liters. And so, put another way, 1 mole of any gas at standard temperature and pressure will have a volume of 22.4 liters. Now, what happens if we take that 1 mole of gas to the bottom of the Marianas Trench? At that spot, the pressure is 109 gigapascal, and the temperature is 1 degree Celsius. So first of all, do we know where this is and what this is, the Marianas Trench? So the Marianas Trench is in the Pacific Ocean, as you can see from the map here, is out near Guam. And it is the largest trench found anywhere on Earth, or I should say the deepest trench. Its maximum known depth is just over 36,000 feet. So being that far down, the pressure ends up being extremely high. So again, that's 109 gigapascal. At 1 degree Celsius. So what's going to happen to our 22.4 liters of gas at that point? So we could do this as an ideal gas law problem, or we could do this as a combined gas law problem. Doesn't matter which way we do it. Both ways should get us to the exact same answer. So let's do this one as an ideal gas law problem. So again, we're solving for volume, so V is equal to nRT over P. So N doesn't change from the previous part, it's still 1 mole. R is still our constant. Our temperature is 1 degree Celsius, which converts very easily to 274.15 Kelvin. And then our pressure needs to be in atmospheres. So we're going to have to take 109 gigapascal and convert that to pascals before we can convert it to atmospheres. So giga, we should recall, means 10 to the 9th. So that's 10 to the 9th pascals in 1 gigapascal. And then we can go to atmospheres. 1 atmosphere is 101,325 pascals. And so we calculate that out. We get 1.1 times 10 to the 6th atmospheres. We can plug that in up here in our equation for pressure. And then it just becomes a matter of doing our calculation and solving for V. And if we've done everything correctly, we get that our new volume, so our volume was 22.4 liters, but because of this new pressure, we're now at 2.04 times 10 to the minus 5 liters. All right, question 3. You can see we're given a volume, a pressure, and a temperature. And we're looking for mass. Again, mass doesn't show up directly, so if we're going to find mass, that means we must be solving for moles. Now we can rearrange the ideal gas law to solve for moles. N is equal to PV over RT. Our pressure of 780 torr has to be first converted into atmospheres. Our volume is already in the correct units of liters. On the bottom, we plug in R. And then the temperature was already given in Kelvin. So if we solve that, we get 1.73 moles. But remember that what we're trying to find here is not moles ultimately, but mass. So we take our mass, our number of moles, and we multiply it by the molar mass from acetylene. Acetylene is C2H2, so we can add that up. We find there's 26 grams in 1 mole of acetylene, and we get a final answer of 45 grams. All right, I'm going to skip ahead for the moment to number 5. So number 5 is pretty similar to the last one of the last ones we did on the lecture slides, because we're looking for the molar mass of some unknown gas. But in addition, I also tell you if the gas is a pure element to figure out what gas it is. But here we're given volume, pressure, and temperature. So it's going to be very straightforward to solve for number of moles. The only one of these that we have to convert is the temperature. Which we can easily do by adding 273.15. And once we do that, we find that we have 0.101 moles. Recall then that all we needed to do to find molar mass was take the mass, which is given in the problem, over the number of moles, and we get a molar mass of 129 grams per mole. And then you would just need to look on your periodic table to figure out what element that is. And so what element has a mass of 129 grams per mole? So that is the approximate mass of xenon. All right, now let's go back up to number 4. And the reason I saved this one for last is there's quite a bit involved in this problem. So take a moment and think about exactly what concepts you need to use to determine how to go about doing this problem. So we know the pressure, although it's in an odd unit. We know the temperature, although we're going to have to convert that. And we're looking for a volume. So ultimately we're going to need number of moles. But the only thing we have is a quantity for the starting material, isooctane. But if you think about what we learned with stoichiometry, if we know the amount of starting material, we can figure out the moles of the product. But in order to be able to figure out that, we're going to need to be able to do two other things. First of all, we're going to have to get from 15 gallons into a more useful unit such as grams. And second, we need to balance our equation. So I'm not going to go through the balancing. We've actually already done this exact reaction before. So there we have it balanced. Our next step needs to be converting this 15 gallons into a more useful unit. So first, we're going to go from gallons to liters. And then we can go from liters to milliliters. Then, using the density, we can go from volume to mass of isooctane. And then finally, we're going to divide by the molar mass of isooctane to get moles. So what's the purpose of this problem? Because as we can see already, it's a very, very involved problem. Well, isooctane is what you put in your car. That's gas. The temperature and pressure I chose, those happen to be the temperature and pressure on the day that in Providence, the day I wrote this problem. So in other words, what I'm asking you in this question is how much carbon dioxide do you produce when you burn through a tank of gas? All right, so we've balanced our equation, and then we found that 15 gallons of isooctane are equivalent to 345 moles. Now we're going to use our coefficients to go from moles of starting material to moles of product. And we get that from our coefficients. That's why we had to balance the equation. And so we find burning our tank of gas is going to produce 2,760 moles of carbon dioxide. Is that a lot? Well, let's find out. So we're going to take our ideal gas law and solve it for volume again. We've done that before. V equals nRT over P. N here is the value we just found, 2,760 moles. R is the ideal gas constant. And then we need to convert. So our temperature was given as 43 Fahrenheit. We need to convert that to Kelvin. Not going to go through the steps for these conversions because I'm going to assume at this point that that's something you're capable of doing. And then we converted our inches of mercury into atmospheres. And we would have done that by going from inches to centimeters, centimeters to millimeters, and then millimeters of mercury to atmospheres. And we get 1 atmosphere. So finally, we can enter all of this into our calculator, and we find that by burning 1 tank of gas, our car will generate a little over 63,000 liters of carbon dioxide. And if it was a warmer day, this number would be even higher.